These are the notes for AP Calculus on the topic of optimization problems. So, to optimize something means to make something the best or the most efficient. And in calculus, optimizing in this context means we're either going to maximize something, find the absolute maximum, or minimize something, find the absolute minimum. So these are the general steps we'll be going through on these optimization problems. So you can refer back here if you kind of get lost in a problem, want to see what you need to do next. So you're going to need to assign variables in the problem if they're not already assigned for you. And some of these will have a diagram to draw. And then you're going to write one or more equations using the information given in the problem. And the key thing is to always figure out the variable that's to be maximized or minimized. That's your main equation that eventually, in order to maximize or minimize it, you're going to take the derivative of. And then if necessary, sometimes that main equation is in terms of two variables instead of just one. So if it is in terms of two variables, then you're going to use substitution to write the variable that's to be maximized or minimized as a function of a single variable. So to get rid of one of those variables, that's where you'll use your second equation if there is one. And then determine the interval that makes sense for the problem. So I refer to this as the common sense interval, because oftentimes they don't tell you what interval to use. So you just have to think of what values actually would make sense for that variable. And then finally, whatever you're trying to minimize or maximize, that main equation, once you have it as a single variable, you're going to differentiate, which means to find the derivative, just like you would for any other absolute minimum and maximum problem. Because remember, differentiation is the process of finding the derivative. And you're again going to find the absolute maximum if it asks for that, or the absolute minimum if it asks for that. And then just don't forget to use correct units. Almost all these problems will give you some units for. All right, let's take a look at some examples here, because this can be applied to all different types of contexts. So this one says we've got a rectangular field. So let's go ahead and draw that. It says it's bounded by a fence on three sides. Fence on three sides, and then there's a stream, a straight stream on the fourth side. So there's our stream, just like a river here. And then you want to find the maximum area. So that's what you're maximizing here. It's going to be our main equation. And then the variables to assign on here, you can see since it's a rectangle, we'll need two variables to start with. So to make it simple, I'm just going to use x here and here, and y right here. So the area, you can see right there, our rectangle, our main equation that we're trying to maximize, is just length times width, x times y. But we don't take the derivative yet to find the absolute maximum because it's got two variables in it. So notice what it also tells you is there's 400 yards of fence, which is kind of like perimeter, except perimeter is the distance all the way around the outside, which would also include the stream. And notice the fence is only on three sides where we put the variables x and y. There's no fence on this side with the stream here. So the 400 would equal, if we add up the sides, we get 2x plus y. And this is our secondary equation that we'll use to get one of the variables, either x or y, out of the main equation. So we can eventually take the derivative of it. So you can take a look and see which one looks easier to isolate. Here, either one would work, but in this case, y is probably a little easier to isolate because all you have to do is subtract the 2x from both sides of the equation. And then we can substitute that in to replace the y right there. So now we'll have the area is x times, we just replace the y with 400 minus 2x. And then you could take the derivative right here, but then that would require the product rule. So instead, let's go ahead and distribute out that x so that makes the derivative a little easier. And so now I'll also write it in function notation so we don't mix it up with those related rates type of problems, which can sometimes seem a little similar. So this is the area as a function of x now. If you distribute out the x, that would give you 400x minus 2x squared. And since this is what we're trying to maximize, now that we have a single variable, as simple as it's going to be, now we take the derivative to maximize it. So a prime of x would equal, derivative of 400x is 400, minus the derivative of 2x squared gives you 4x. In this case, that will never be undefined. There's no negative exponents or denominators. So we just see what makes it 0. You can isolate the x, or here it might be faster, so you can just factor out the 4 as a GCF. And then what you're left with is 100 minus x. So here, 4 is never 0. If you set 100 minus x equal to 0, you get x equals 100. So that's our only critical number on this one. And then here's where we draw our common sense interval. When we draw the number line, just like you would for any other absolute minimum or absolute maximum problem. In this case, it's the absolute maximum we're looking for. So the common sense interval is based on your variable, your whatever your maximize and minimize is in terms of. In this case, it's in terms of x. So just think, what values of x would actually make sense? Well, x is the distance here on each side of the rectangular field. So x can't be negative, and it can't even be 0. It has to be some positive value. So this is the most common lower limit of the number line here on these optimization problems. Most of the problems, only positive answers make sense. So that's the case here. But on this one, they don't really give you a particular upper limit of what x could equal. So a lot of times there's not. So you can just put your one critical number, 100 there, and then label it a prime of x. 100 makes the derivative 0. And then if you plug in, you actually could substitute in 0 here because it's not a critical number. 100 minus 0, that's positive. Here, if you put 101, 100 minus 101 is negative. So what this shows us is the area, a of x, since its derivative is positive, the area would be increasing as you make x larger and larger until you get where x is 100. And then if you start making x larger than that, then the area of that rectangle starts decreasing. So if you sketch a little picture of that, increasing and then decreasing, we're looking for the absolute maximum. And you can see there's only one possible place that can happen, right at 100. And that's what happens on a lot of these. Not all of them, but a lot of them, there's only one possible thing once you sketch a graph where it could be. So we know it has to have a maximum when x is 100. Now sometimes I might ask for the dimensions, in which case x would be one of the dimensions, and you could plug it in right here to find y would be the other dimension. But here it actually asks for what is that maximum area. So the last step here, let's go back to the original equation and substitute in 100. Since we know the area is maximized when x is 100. So I'm just going to use this form right here. So that'd be 400 times 100 minus 2 times 100 squared. So 400 times 100 gives you 40,000. 100 squared is 10,000 times 2, 20,000. So 40,000 minus 20,000 gives you 20,000. And the units here for area, since fence is in yards, area is two-dimensional, so this would be yards squared. So that's the maximum area of this rectangular field. All right, let's take a look at the next example. On the next one, it says a cylindrical tin can. So here we can draw a diagram of this one as well, shaped like a cylinder. And then it says it's got an open top. So I'm just going to write open here to remind myself there's no surface right there. It's designed to hold 27 cubic centimeters. Okay. So here when you're assigning your variables on your diagram, if you have a geometric solid like here that we've got a cylinder, it's probably easiest if you just use the normal variables that would be used in their formulas. In this case, the height of the cylinder and then the radius of the cylinder, R and H. And then what the 27 cubic centimeters is giving you, notice that's volume. And the volume of a cylinder, remember, is the area of the circle, pi r squared times the height. But that's not our main equation. That's just going to help us out because it says what radius will minimize the amount of tin needed. Well, the amount of tin, that would be the surface area. So here we're trying to find the minimum surface area. So that's going to be our main equation. S equals. Well, the surface area for a cylinder, notice it just says the top is open, so we can assume the bottom is closed here. So that's just the area of the circle, which is pi r squared. Notice if it had been closed on the top also, it would have been another plus another pi r squared would have made it 2 pi r squared. Plus, remember the part that wraps around the cylinder? On the side, you can just get from the circumference, which is 2 pi r, times the height. So again, this is what we're trying to minimize. So this is what we eventually need to find the derivative of. But just like the last problem, notice it's in terms of two variables instead of just one. So that's where we can use our other equation, our secondary equation, to help us get rid of one of those. So you could solve for RH, but which one looks easier to isolate here? Well, for a couple reasons, it's probably easier to isolate the h by dividing by pi r squared. First reason is you don't end up having to take the square root of both sides and then needing a plus or minus. The second reason is when you solve for h, notice there's only one place we have to substitute into, as opposed to if you solve for r, you'd have to substitute in two different places. So we'll substitute in for h right there. And so now we'll have the surface area is pi r squared plus 2 pi r times h, we just figured out, is 27 over pi r squared. And so now we can write this S of r. Surface area is just a function of r. So you've got pi r squared. And then notice what simplifies here. You can see the pi's reduce out, and one of the r's reduces out. So you get 2 times 27, which is 54. And you could write it 54 over r. However, then when you take the derivative, you'd have to use the quotient rule, which is fine, but it's easier if we just move this r up to the numerator. So this is r to the first. When you move it up, instead of 54 over r, that's the same as 54 r to the negative 1. That way we don't have to use the quotient rule, we can just use the power rule, which is a little more efficient here. So now, since this is what we're trying to minimize, now it's in terms of one variable. So now, again, the key concept here, whatever you're trying to maximize or minimize, that's the equation you take the derivative of. So when you take the derivative of this one, derivative of pi r squared is 2 pi r. And then using the power rule, bring down the negative 1 times 54, 54, r to the negative 2. And then to simplify this, let's use factoring on this one. So notice you can factor out a GCF of 2, and they both have r. Remember, you factor out the lower exponent, so r to the negative 2. And then what you're left with on the first one, we've still got the pi, and then r to what power? Well, one way to look at this was r to the first here. We factored out r to the negative 2, and when you multiply these back, they have to add up to be 1. So 3 and negative 2 add up to 1. Or you can think 1, when you factor it out, it's like dividing by it. So 1 divided by this, so where you subtract the exponent, so it'd be 1 minus negative 2 becomes 1 plus 2, which is 3. And then minus here, the r is completely factored out. We took out a 2 out of the 54, gives you 27. All right, and then we almost have it simplified all the way. So now we just have 2 times pi r cubed minus 27, and then now you can move that r to the negative 2 that we factored out all over r squared. So this derivative could be undefined. So the critical numbers are where it's 0, the numerator 0, or where it's undefined. So if you set the numerator equals 0, notice in order to solve that for r, you would first add the 27. So you get pi r cubed equals 27. Then you would divide by pi. So you get r cubed equals 27 over pi. And then you would take the cube root of both sides. Get rid of the cubed. So r, cube root of 27 is 3, and then the cube root of pi, and just leave as the cube root of pi. And then on the denominator, you just get r equals 0. So then we draw our common sense interval here. In this case, the interval is for r, since our surface area is in terms of r. Again, r has to be some positive value to make sense for the radius here, so we put 0 with the parentheses. Has to be something positive. And again, there's no specific upper limit on what the radius it can be that it gives us based on the wording or the diagram, which a lot of times there isn't. So you would just have our critical number 0 here, and then 3 over the cube root of pi. And then when we label this S prime of r, the only difference here is we won't be able to test 0 because 0 is one of our critical numbers. It makes the derivative undefined. And this one came from the numerator, makes the derivative 0. So to see what you could test between 0 and 3 over the cube root of pi, well, the cube root of pi is like the cube root of 3.14, which cube root of 1 is 1, cube root of 8 is 2, so it's 1 point something. Into 3, notice that's more than 1. So you could safely test 1 here. And notice that when you test in the derivative, you don't have to worry about the denominator. That's squared, so that's never going to be negative. So when you test 1 right here, 1 cubed is 1 times pi. That's pi minus 27. Well, that's like 3.14 minus 27 is negative. Then here, you could test something huge. There's no upper limit or other critical number. You could test 100 or something. 100 cubed times pi is minus 27. That's definitely positive. So what this is showing us is the surface area, S of r, as we make the radius larger and larger. To start with, that surface area starts to decrease, but once we make the radius exactly 3 over cube root of pi, then the surface area starts increasing. So we'll sketch the graph. It'd be decreasing and then increasing. So again, you can see there's only one place the absolute minimum could be, right here, when r equals 3 over the cube root of pi. And if it asks you for what is the minimum surface area or what is the amount of tin, then you'd have to plug it back into the original equation like we did in the first one. But here, it's only asking for the radius. What radius will minimize the amount of tin needed? And we just found that. We just have to put the units on it. Notice since volume was cubic centimeters, the radius is just one-dimensional, just a length, it would just be centimeters. All right, let's take a look at the next example here. So this one already gives you the graph, and it says it has the rectangle has its two lower corners on the x-axis here and here, and its two upper corners on the curve. So this is the graph of y equals 12 minus x squared. So the two upper corners are there. So this is just some point right here on the curve. We can call it xy. And it says for all such rectangles, because you see this is not the only one. You could also have one right down here. You could have one up here. There's a lot of different rectangles you can get with these restrictions. As for what are the dimensions of the one with the largest area? So largest area is just another way of saying you want the maximum area. So in order to get the maximum area, well, in this case, since it's on the x and y axis, x and y will be our variables. So notice this just represents the y coordinate right here. And from here to here, that represents the x coordinate. And because of the symmetry of the graph and the rectangle, this is also, from here to here, also the x, same length x. So our area of our rectangle here, notice would be, this side is 2x times this side is y, length times width. So 2xy. But again, before we take the derivative to find the absolute maximum, we can't do that yet because it's got two variables, x and y in it. But in this case, it's a little easier. They already give us the second equation. Because we know this point's on this curve, it has to satisfy this. And it's already solved for y, so you can just substitute in for the y, the 12 minus x squared. So now the area would be 2x times 12 minus x squared. And again, you could take the derivative here, but then you'd have to use the product rule. So it's probably a little easier if you just distribute out the 2x first. And then we can also write this as just a of x now. Area just as a function of x. 2x times 12 would be 24x minus 2x cubed. And then since now it's in terms of one variable, and we want to maximize it, now is when you would take the derivative. So a prime of x would be 24 minus, bring it down to 3 times 2 is 6x squared. And then this one's never undefined. There's no denominator of negative exponent, so you just want to see what makes it 0. So notice here you could factor out a 6, and you're left with 4 minus x squared. And then you can see that fits difference of perfect squares factoring. So since the 4 is first, the 2 would be first. 2 plus x and 2 minus x. So this one, 6 is never 0. This one gives you x equals negative 2. And this one, x equals positive 2. So when we draw our common sense interval here, again, x is just this distance here, so this has to be something positive. But again, there's no upper limit on x. Well, actually, there is kind of on this one, but you don't have to find it. It's really wherever this intersects right here. So you can see negative 2 is definitely not a reasonable answer, but 2 is definitely less than this. Where this would be if you said equals 0 is the square root of 12, but that's not going to affect it at all here. So we just have 2. And then label this with the derivative a prime of x. 2 makes the derivative equal to 0. And then here you could test 0 or 1, because 0 is not a critical number here. That would just be positive. 2 plus 0, positive. 2 minus 0, positive. Positive times a positive is positive. Here you can test 3. 2 plus 3 is positive. 2 minus 3 is negative. Positive times a negative is negative. So what this shows us is the area of this rectangle here would be increasing up until when x is 2, and then after, if x gets bigger than 2, then the area starts to decrease. And so you can see the maximum that we're looking for would have to be when x equals 2. But it asks for the dimensions. So now we know x is 2. That means this x is 2, so 2 plus 2. One of the dimensions is 4. And to get the other dimension, y, the height of the rectangle, it would just be 12 minus, now we know x is 2, so 2 squared gives you 12 minus 4, so y is 8. So now we know the dimensions. This side is 4, and we don't have specific units here, so it would just be 4 units by, this side is 8, so 8 units. All right, let's take a look at another example here. So here we've got another cylinder one. It's just a little different than the other one. It says consider all right circular cylinders. So we can draw our cylinder here off to the side. For which the sum, remember in math, sum means you're adding, of the height and circumference is 24. So what that's saying is, again, since it's a cylinder, we'll just use the radius and the height to label it. It says the height, the sum of the height, so height plus the circumference has to equal 24. And then it says, what is the radius of the one? So we're looking for just the radius here with the maximum volume. So that's our objective here, to find the maximum volume. So volume is going to be our main equation. Well, again, it's just a cylinder, so it'd be pi r squared, area of the circle, times the height. But again, we don't take the derivative yet because it's got two variables. We need it to be just in terms of one. So on this one, so that we don't introduce an extra variable c, remember the circumference is just 2 pi r. So you can replace that circumference there. So the height plus 2 pi r has to equal 24. And then you can isolate either one to substitute in, but probably the h is going to be easier to isolate. And notice it'll be a little easier when we substitute in because then we don't have to square it like we would for r. So h, if you just subtract the 2 pi r, would be 24 minus 2 pi r. And then you can substitute that in to replace the h in our main equation, volume, which is what we're trying to maximize. So now we've got the volume is pi r squared times 24 minus 2 pi r. And again, now it's in terms of a single variable, so now you could write it as v of r. And if we just distribute this out, then we won't have to use the product rule. So 24 times pi r squared would be 24 pi r squared. And then minus pi r squared times 2 pi r would be 2. Pi times pi, notice, gives you pi squared. R squared times r cubed. So now we've got our volume in terms of just one variable, the radius, and that's what we're trying to maximize. So that's what we would take the derivative of. So v prime of r, 2 times 24 would be 48. Pi, reduce the exponent by 1, r, so just pi r. And then 3 times negative 2, so negative 6 pi squared r squared. This one doesn't have any negative exponents or denominators, so we don't have to worry about being undefined. So you just set it equal to 0. And notice you can factor out a GCF of 6 pi and an r. So when you do that, let's see what's left. Well, we still have 8 here, because it was 48. But we factored out the pi and the r, so that's it. Minus, on this one, we took out the 6. We took out a pi, but remember it was pi squared, so there's still one more pi left there. And it was r squared. We only took out 1, so we still have an r there. So if you set this one equal to 0, you just get r equals 0. And if you set this one equal to 0, you'd first add over the pi r, and then divide by pi, so r equals 8 over pi. And then let's check to to see our common sense interval, see if those answers make sense. So again, it's in terms of the radius. The radius has to be something positive. But again, there's no upper limit that we know for sure on the radius. So we would just put 8 over pi, which is close to 8/3, and label it v prime of r. 0 was a critical number, though, so it makes it 0. So we can't test that. But you could test 1. That's definitely less than 8/3. So 1 right here would make this one positive. 1 right here would be 8 minus pi. 8 minus 3.14, that's also positive. Positive times a positive is positive. You test something greater than 8/3, because 8/3 is roughly 2 and 2/3. So you could test 3 if you want, or 4. So 3 right here would be positive, but 3 times pi is more than 9. So 8 minus 9 point something would be negative. So positive times a negative is negative. So this shows you the volume, V of r, would be increasing and then decreasing. So the graph would look something like this. And since we're looking for the absolute maximum, it would have to be right there. And notice it just asks for the radius, and that's what we have right here. This is r. So the radius is 8 over pi. If it asks for what the maximum volume is, you'd have to plug that into the original equation. But here, in the units, since the height and circumference are centimeters, radius is also just one-dimensional, so just centimeters. All right, let's take a look at a few more here. So the next one, we've got the diagram. It says the figure represents a square sheet of cardboard with a side length of 30 inches. So it's a square, and so this side is 30 from here to here, and this side is also 30. The sheet is cut and pieces are discarded, and you can see the white pieces are the ones that are going to be discarded here. When the cardboard lid is folded, it becomes a rectangular box with a lid. So you can see once you discard those, you can fold these up here, and this becomes the lid right here. The pattern for the rectangular box with a lid is shaded in the figure. So again, it's the shaded part, that's the box. 4 squares with a side length x. So all of these 4 have a side length of x. And 2 rectangular regions, these are the 2 rectangles, are discarded from the cardboard. And we want to determine the length of x needed in order to maximize the volume. So that's what we want to maximize the volume. So in general, the volume of a box is length times width times height. But because of the way this is labeled here, we can get all of those in terms of just x. So let's start with the length here. Notice this starts out as 30, but we're going to cut out these 2 x's, so that would be 30 minus x minus x. So our length right here would be 30 minus 2x. And in a similar way, notice this side starts out as 30. We remove the x's there. So it'd be 30 minus 2x, but that would cover both of these, right? And see, since this is the lid that goes right on top of the base here, these have to have the same length. So the whole thing together would be 30 minus 2x, but we'd have to divide it by 2. So that would give you 30 divided by 2 is 15, negative 2x divided by 2 is negative x. So that means from here to here, 15 minus x. And you can see that becomes the width of the box. It would be the same from here to here too, 15 minus 2x, or 15 minus x. And then the height, when you fold it up, you can see is based on the size of the squares. That's just x. So here we don't need a second equation because it's already in terms of a single variable, x. So you could take the derivative right now, since we're trying to maximize the volume, but that would require the triple product rule. So instead, let's go ahead and multiply this out to make the derivative easier. So first I'm going to multiply these 2 binomials together. So 30 times 15, well 3 times 15 is 45, add the 0, so 450. Then we get negative 30x here, and another negative 30x here, so that's negative 60x. And then negative 2x times negative x is positive 2x squared. But that whole thing is still multiplied by x. So now you can just distribute the x times all those. So now we've got our volume. It would be 450x minus 60x squared plus 2 x cubed. And so now we can find the derivative, because this is what we're trying to maximize. So v prime of x would be 450 to the power of minus 120x plus 6x squared. So again, you can see this one would never be undefined. There's no denominator or negative exponents, so you just see what makes it equal to 0. And to solve this one, it's probably easiest if you first take out the GCF. Notice that 6 goes into all of these here, so you could factor out a 6. And then I'm just going to reorder the terms so they're in standard form with the x squared term first. So the x squared minus, if you take 6 out of 120, you're left with 20x. And then this is a plus because it was a positive 450. Well, 6, you can do this a couple ways here. So one way you could divide it first. Divided by 6, you might not know what that is right away, but if you divide it by 3, that would be 150, right? Because 45 divided by 3 is 15. And then you divide it by 2, 150 divided by 2 is 75. And then to see if this factors, are there factors of 75 whose sum is negative 20? And there are. You could use negative 5 and negative 15. Multiply to be positive 75, add up to be negative 20. And we can use the shortcut here since there's a 1 in front of the x squared there. So we get a couple answers here. X equals 5, x equals 15. So now when we draw our common sense interval, again, x has to be something positive for it to make sense and actually get this box. But here, notice, based on this, if you look at this side here, these x's can't go beyond halfway, otherwise you wouldn't have a box. So half of 30 is 15, so it can't be 15. It has to be smaller than that. And so because of that, 15 is actually not a reasonable answer, but 5 is. So then when you label this v prime of x, makes it 0, so does 15. And then we can test. You could test 0 here. 0 is not a critical number. 0, that'd be negative times 0 minus 15 negative times a negative is positive. Here you can test 6 minus 5 is positive. 6 minus 15 negative. Positive times a negative, negative. So this shows us the volume of our box here would be increasing and then decreasing. And so you can see there's only one place the maximum could be, right at 5. And that's what it asks you for, determine the length of x. So x would have to equal 5, and the units here are inches. Okay, the next one, you actually don't need to draw a diagram at all here. And there's a little typo on there, I think, so I think it might have said 0 to 3 for the interval here. It should be 0 to 5. So it says the speed of a runner in miles per hour along a straight path is modeled by this. So they give you this. This is the function for speed, and m is the runner's distance in miles from the start of the path. What is the maximum speed of the runner on 0 to 5? So So we're trying to maximize speed, and they already give us the speed equation. There's no need to draw a diagram. And notice it's already in terms of a single variable. So we don't have to substitute in. So we can take the derivative right away on this one. So g prime of m. Now, there's a couple ways to handle this here. You could use the product rule on this. That's one way. But that's not necessary because there's no variables on the outside. It's just a constant 1/12. You could distribute the 1/12 first and then take the derivative. Or you can take the derivative right now, because remember, a constant out in front just stays there. So you can actually just leave the 1/12 there. When we take the derivative, it just stays there as a coefficient out in front. And then it's a little easier to just take the derivative of each of these terms separately. So this would be negative 6m squared plus 30m minus 24. And the derivative of 8 by itself is 0. And then when you set this equal to 0 to make it easier to solve, notice you can factor out a negative 6 out of all these times the negative 1/12, reduced to negative 1/2 on the outside. And then we'll be left with positive m squared. If you take out a negative, in this case negative 6, it changes the sign of all these, so this one's going to be negative. Take out a 6, so you're left with 5m. And take out the negative 6, and you're going to be left with positive 6 times 4 is 24. And then you can factor that trinomial. And factors of 4 that would be negative 5 would be negative 1 and negative 4. So we have two critical numbers, m equals 1 and m equals 4. And if I had added 3 there, you can see the 4 would have been irrelevant, but 1 and 4 in this case are both in the interval from 0 to 5, so they're both critical numbers there. So we can draw our common sense interval, except this time they tell us the lower and upper limits. It just tells us it's from 0 to 5. With brackets, because it's got the equal to's. And both 1 and 4 are in there. So for g prime of m, label your number line here, both of those, 1 and 4, make the derivative 0. Here you could test 0 since it's not a critical number. 0 minus 1, that would be negative. 0 minus 4 is negative. But then don't forget this negative 1/2 on the outside as well. So that's 3 negative numbers together, multiplied together, is going to be negative. Then here you could test 2, that's still negative 1/2. 2 minus 1 is positive, 2 minus 4 is negative. 2 negatives times a positive is positive. And here you could test 5 because it's not a critical number. So it'd still be negative. 5 minus 1 is positive, 5 minus 4 is positive. 2 positive times a negative is negative. So what this shows us is the speed, which they call g of m here, would be decreasing, and then increasing, and then decreasing. So it's like this: decreasing, increasing, decreasing. So this time for the maximum, notice there's actually a couple places it occur. A lot of these there's only one place, but here it could occur at 4 or at 0. So we have to compare for the absolute max which of those is larger by plugging those into the original function. So we have to compare g of 0, which you can see if you substitute in 0, that's going to, for m, that's going to wipe out all these terms here except for the plus 8. So that's just going to be 8. And then we need to compare that with g of 4. So we've got 1/12 on the outside. And then what I'm going to do here to make the calculations a little bit simpler, so I don't have to do 4 cubed times -2, which you could do. Just a little strategy to make it easier. They're all going to have at least 1 4, right, when you plug it in there, because this says m to the third, m squared, and m. So what I'm going to do is actually just factor out the 4 times the 1/12, so I'll make it 4/12, which we're going to reduce. And then we'll just have 1 fewer 4 when you plug it in. So then we'll just have -2 times 4 squared plus 15 times just 4, and then minus 24. 4/12, notice reduces to 1/3. Oops, I forgot the, there's also this +8 here. So I have 1/3, and then if we simplify what's left in here, that's 16 times -2, that's -32. 4 times 15 is 60, minus 24, and don't forget the +8. So that's 1/3 times, that's 60 minus 56 is 4. So this works out to be 4, so this becomes 4/3. Plus 8 is 24/3. Gives you 28/3. And the units here, notice we plugged into G, and the G, it says the speed in miles per hour, so this would be miles per hour. Oh, we have to see which one's greater for the maximum. Notice 3 goes into 28. 9, so this is the same as 9, it gives you 27 and 1/3, which is bigger than 8 for a G of 0. So we can say the maximum speed is either 28/3, or you could write it as 9 and 1/3, and the units would be miles per hour. All right, let's take a look at the next one here. One more. This one's a little different because it says cars enter a line for Dutch Bros at a rate. So it's already giving you, remember, rate's another word for the derivative. Even though it's written as E of t, that's actually the derivative. You can also tell it's derivative because look at the units. It's cars per minute. So that's already the rate that cars are entering the line. And it says cars leave the line at Dutch Bros at L of t, 2t plus 4 cars per minute. I should have put, I left off a few words here. Leave the line at a rate of L of t, 2t plus 4 cars per minute. And then what time on the interval 0 to 5 is the number of cars in Dutch Bros a maximum. So we're maximizing the number of cars, but we already have the rates in cars per minute. So the overall rate would be the rate they enter minus the rate they leave. So the rate they enter would be t squared minus 5t plus 10. And again, these are already the derivatives, so we don't need to find the derivative again on this one. Minus L of t, 2t plus 4, but then notice you're subtracting the whole thing, so you need parentheses there. So if we simplify that, that would be t squared. Then we have negative 5t, and this is negative 2t, gives you negative 7t. And then 10, this becomes minus 4, gives you positive 6. So that's our overall rate there. So that's what you would set equal to 0. And then you can factor that into factors of 6. That would to be negative 7 would be negative 1 and negative 6. So we get t equals 1 and t equals 6. But then look at the interval 0 to 5. So 6 is outside that interval, so it's irrelevant for this problem. And then when you draw your number line, it's already given you the common sense interval here. They tell you the interval is from 0 to 5. And 1 is the only critical number in there. We got it. So then your overall rate here, which is E of t minus L of t. 1 makes the overall derivative 0. Here you could test 0 because it's not a critical number. 0 minus 1, that's negative. 0 minus 6, negative. Negative times a negative is positive. Here you could test 2 minus 1 is positive. 2 minus 6 is negative. Positive times a negative is negative. So what this tells you is the derivative of the number of cars. So the number of cars in line at Dutch Bros would be increasing and then decreasing. And so you can see in this case there's only one possible place that can happen, right at 1. And that's what it asks for, at what time. So that'd be t equals 1, and the units for time here are minutes. And that concludes the notes for AP Calculus on the topic of optimization problems.